Great. Hello, everybody. My name is Alessia, and I'm the lead lecturer here at Pearl Street Studio. Welcome to our lecture on an energy resource comparison. So in this unit, we have discussed 9 different resources used for generating electricity and for storing energy. So the goal of this lecture is to help people understand some of the trade-offs between these 9 resources. Now, before I dive in, I did want to mention that this is lecture 10 in our course Introduction to the Electricity Industry. If you haven't already, we highly recommend that you go back and watch our energy resource lectures on coal, crude oil, natural gas, geothermal, nuclear, hydro, wind power, solar power, and batteries, as this lecture is going to be referencing or directly referencing the material that we went over in those lectures. No worry if you haven't watched them, we will add a link in the notes to the YouTube videos for these previous lectures, but you can also find them by visiting our website at pearlstreetstudio.org. Awesome. Well, let's dive in now. Okay, so let's start by the generation profile. So before we go into the comparison, I'm going to go over the definitions of the different types of the different generation profiles. So a dispatchable resource is a resource where the rate of electricity generation, or how much electricity is being generated, is controllable by an operator. So an operator can ramp it up, ramp it down as they like. And then within dispatchable, there are 3 subcategories. There is baseload, intermediate, and peaker. So a baseload resource produces electricity at the same rate for 24 hours a day. These are resources that usually take a couple of hours to ramp their power output up or down, and they're usually a bit lower cost than some of the other resources. Then there are the intermediate power plants, and they typically produce electricity over a part of the day, 8 to 16 hours roughly. And then there are the peaker plants. These are typically the most expensive plants, but they can very quickly ramp up their electricity production or very quickly ramp down. So this is useful when there are these big spikes in electricity demand from consumers. And peaker power plants typically only produce electricity during the highest demand hour of the day. Then the last one is intermittent here. And intermittent resources are resources where their generation output cannot be controlled by an operator, and their generation is dependent on the weather. So now that we've gone over those definitions again, let's take a look at our comparison. So coal, as we mentioned, is a dispatchable baseload resource, because typically it takes an hour or two for coal-fired power plants to change their power output, so they're typically run just continuously at the same rate throughout the entire day. Then for crude oil plants, looking specifically at combustion turbines, we're going to ignore diesel generators here because they don't play a big role on providing electricity at a large scale. But looking at combustion turbines, they can turn on very, very quickly, but they are very expensive to run, which we'll discuss a bit more in a moment. So they are typically operated as peaker, just running for maybe an hour a day. Then of the different natural gas power plants, remember we have 3 different kinds. We have simple cycle, we have combined cycle, and then we have cogeneration. And so cogeneration, since it is also providing a heat source for some other industrial process, or building heat, let's say, as well, cogeneration is typically operated consistently throughout the day as a baseload resource. Then combined cycle plants, since they operate more efficiently and therefore more cheaply than simple cycle, they can typically operate as an intermediate load or as a baseload resource, depending on what other power plants are available. And then the simple cycle natural gas power plants, they can ramp up and down their production of electricity very quickly, but they are less efficient and more expensive to run. So they're typically only run for an hour or 2 per day during those peak times. Then there's the geothermal resources. They are typically operated as baseload resources, even though operators can change their output in order to maintain the underground temperature and pressure of the geothermal resource. These power plants are just typically operated consistently throughout the day. Nuclear power plants also take a couple hours to adjust their power output, so they are typically operated consistently throughout the day as a baseload resource. Then hydropower. Hydropower is very, very flexible. It can be a baseload, intermediate, or a peaker power plant. And this is because all that needs to be done is to open the intake or close the intake, which can very quickly let water down from the reservoir to spin through the turbine blades and very quickly generate electricity in a matter of minutes. Then wind and solar are both intermittent resources, as we've discussed. Wind is dependent on local wind patterns in a region, and solar is dependent on the sunlight and the daylight. And then finally, battery resources. Even though they don't generate electricity, they can store and release it at a later time, and batteries can respond very, very quickly, actually in less than a second. And so they are typically considered peaker resources, so they can help generate electricity, release energy to the electric grid on very, very short notice. Okay, so that is the generation profile of the different resources. Now let's go over the storage capability of the different resources. So production from a pipeline fuel here. This is a power plant that receives a continuous supply of its fuel from a pipeline, and this is really only applicable to natural gas. And this is because natural gas has a very large volume, so it's difficult to store on site. So it's typically transported and stored within pipelines. Then there's production from a stored fuel. So this is being able to store it in barrels or in large containers on site. And this is applicable to nuclear, crude oil, and coal. Coal can just be stored in these very large metal containers on site. Crude oil can be stored in large metal barrels, and then nuclear fuel is stored in fuel assemblies, like we had discussed in the nuclear lecture. And then the last category is energy storage. So energy storage systems are not a new source of energy. Instead, they store energy that was generated previously and can very quickly convert it into electrical energy and have it sent out to the electric grid. So this is applicable for hydropower, because remember they have that upper reservoir where they store a bunch of water, and then batteries are under the same category. Now for geothermal, wind, and solar, these three resources don't have a storage mechanism themselves. They are just producing electricity based on natural conditions. In geothermal's case, the Earth's heat. For wind patterns, and solar, the time of day and the weather conditions. All right, so those are the different storage capabilities of these different resources. Let's next go on to location dependence. So the build out of coal-fired power plants, they are not location dependent. It is pretty easy to transport coal into most locations around the world. So coal-fired power plants can be built out pretty much anywhere. Same with crude oil, the combustion turbines used with certain crude oil products. They can pretty much be built out anywhere, and trucks can bring out the fuel to the site. So pretty flexible. And then with natural gas, a natural gas power plant can pretty much be built anywhere. But the reason why we have a little asterisk here is because even though natural gas power plants are technically not location dependent, they do typically require a pipeline that has a connection to that natural gas power plant. And if there is no pipeline that's already built out in a region, it can be a very, very big cost inhibitor to build out a natural gas power plant, and then also have to build out a brand new pipeline to it if there aren't already pipelines that are nearby. So I'm going to say it's no-ish. It's a little bit location dependent based on pipeline availability. Then geothermal is location dependent, even though there is geothermal heat that exists all across the planet. It is constrained to certain regions throughout the world where that geothermal heat is much higher, it's much hotter, closer to the surface of the earth, because it gets very, very expensive to drill down further. The nuclear power plants, they are not typically location dependent. Uranium fuel can be mined anywhere and then processed anywhere and then sent out to power plants pretty easily, no matter where they are. On hydropower, it is location dependent because it needs a region that has a big enough elevation gain where those turbines, when there's this elevation gain, when water goes down here, there has to be enough of that drop to actually spin large hydro turbines to generate electricity. And they also need an area that has some water resource, like a river. And then wind is location dependent. It's the best regions for wind are the regions that have strong and consistent winds. This is pretty common up by the Scandinavian countries, where out on the water and on the coastline there is pretty strong continuous wind out there. But then in other regions, typically more inland, the wind isn't as strong. Then solar is also location dependent, even though it can be economically deployed in most regions around the world. Solar generation is highly dependent on the region, and I think the example that I had used back in the solar lecture is if you had the same set of solar panels that were in Egypt versus the same set of solar panels that were in Norway, those solar panels in Egypt would generate significantly more electricity because Egypt has a lot more exposure to, or has much higher levels of solar irradiance year-round in comparison to Norway. And then finally, batteries. Batteries are not location dependent. They can be pretty much put anywhere and function the same. Okay, let's go over the next section. This is speed to deploy. So this is something that I didn't discuss as much in the past lectures. I think I briefly discussed it in some of them, but I did want to use this as a comparison. So here, a fast deployment of a resource, of a brand new generation resource. So you're building it from scratch. A fast deployment would be in less than 2 years. A moderate timescale would be 2 to 5 years, and a slow deployment would be more than 5 years. Now, one of the things I do want to note, these are generally including the permitting processes, but there are some regions and countries around the world that have a very, very long and tedious permitting process for building out these new projects. Now, that really gets into some policy weeds, but here with these time frames here, I am assuming I would say a semi-average permitting time of maybe a matter of months or at most a year to get something permitted. And then this also includes construction time and design, etc. So for the fast, the resources that can be deployed very, very quickly, we have diesel generators, which is a crude oil product. Diesel generators are they're very small, they're manufactured in a factory, and they can just be delivered by a truck to a location within a matter of hours or days to where it's needed. Then onshore wind is also relatively, can be in the time frame of less than 2 years. Sometimes it can move over into the moderate time frame depending on the permitting process, but generally onshore wind doesn't take as long to deploy. Solar is also very quick because once the solar panels have been manufactured in a factory, it's quite easy to ship out the solar panels to a location and then just install them either on a rooftop or on the ground. And then batteries also can be deployed very quickly. Once the battery has been manufactured in a factory, it can be quite easily set up anywhere. And then for the resources that take 2 to 5 years, these are the resources that don't have as many factory components. So the resources that can be built very quickly are typically mostly assembled in a factory. Most of their parts are designed in a factory, so it's this very quick product build out. But with coal-fired power plants, crude oil, natural gas, geothermal power plants, while these do have some factory components in their design, there is often certain aspects of the power plants that are custom designed, that aren't necessarily built in a factory, so they do typically take longer to build out. And typically they're also bigger. These resources tend to be bigger and can produce more electricity than these resources here. So hence they take a long time. And then wind offshore, even though wind turbines offshore are not all that different from wind turbines that are onshore, typically it's a lot harder to construct offshore in the ocean than in comparison to onshore. So that's why it takes a bit longer. And then the resources that are slow to build, 5+ years, and these two resources can get to 10, or even in some really bad cases 15-20 years, are nuclear and hydro. And there are two main reasons behind this. It is safety and scale. So nuclear has a lot more permitting and regulation that it has to go through, just because nuclear waste has the potential to be so detrimental. So there's a lot that nuclear power plants have to go through, and they're also tend to be built out very, very large historically. And then hydropower plants, it's not as much the safety aspect, it's more the scale. These hydropower plants lead to massive ecosystem disruption in the region. Sometimes certain communities have to be displaced, they have to move to a different area, so these things can take a very, very long time to happen, and then building out a dam for a hydropower plant is a massive construction project, hence why it takes so many years. Okay, now let's go on to the capital and operational costs. So I think this is the most interesting section, in my opinion. So remember, the capital cost is the one-time upfront investment to build out the power plant itself, while the operational costs are the ongoing expenses that it costs to run the power plant. So if you remember back to our previous lectures, remember dollars per megawatt. A megawatt is the equivalent of the how can I put this? The size of a power plant. How much electricity can it generate at a given moment? So the more megawatt, the higher the megawatt rating of a power plant, the bigger and the more it can generate. So that's why it's in these per megawatt units. And then the operational costs are in megawatt hours. So this is a singular unit of electricity that can be consumed, not a rate. This is a rate of electricity that can be generated or consumed. This is a total amount of energy that can be consumed. So looking at the capital costs here, the most expensive projects, certain hydropower projects, if we look at this more expensive upper end, can be really expensive. Nuclear tends to be up there. Historically has been a very expensive resource to build out. We also look at some geothermal projects have historically been quite expensive, and so have coal-fired power plants. Now, if we look at the other resources, they generally have lower to moderate costs in the range of about $1 to $3 million per megawatt. So you see these values with the different natural gas power plants here. You see that for the lower end of the cost of hydropower plants, and then wind and solar here. And then if we look over at operational costs, by far the most expensive resource is crude oil. Crude oil power plants are the most expensive because they use crude oil products that have competing resources. So for example, combustion turbines the power plant that uses kerosene or naphtha. But kerosene is jet fuel, and so there are competing resources, and arguably kerosene is more valuable to be used as jet fuel, since there isn't really another alternative, than to be used to generate electricity, because generating electricity can be done with so many other resources, hence why it's so expensive. Now, if we look at the more moderate cost power plants, we can see simple cycle natural gas power plants are here, coal-fired power plants, nuclear's in this moderate cost, the upper end of geothermal, and then the upper end of onshore and offshore wind can have more of these moderate costs. Now, if we look on the low end, we can see that onshore wind and the lower end of offshore wind can be quite cheap. All the types of solar can be quite cheap, but especially the utility scale / solar farm level of or scale of solar. Also, if we look at combined cycle and cogeneration natural gas power plants, those can be quite cheap as well, but I did want to note that these are numbers for the United States, and in the US, natural gas tends to be much cheaper than it does in most other countries around the world. And then also, I guess if we look at the lower end of geothermal, it can be quite cheap as well as the operational costs of hydro. Okay. So that, I'm pretty much leaving batteries out of it as the last note. It's a little bit how their operational costs and capital costs are calculated are a little bit different. So we can discuss that in more detail in a future lecture. All right, let's go on to the next section, supply chain vulnerabilities. So if we look at this, it is split up into fuel and manufacturing. So for coal, as we discussed in the coal lecture, coal can be sourced from many, many different countries around the world. So there aren't a lot of concerns about the fuel supply chain for coal. And the power plants don't have a lot of concern in supply chain vulnerabilities. But with crude oil and natural gas, both these resources, since they're often fracked for together, crude oil and natural gas, they are typically imported / exported from a small set of countries throughout the world. There are really 10 countries that own most of the fuel supply chain for these two resources. So there are worries about price volatility because of these very concentrated supply chains. Geothermal does not have serious concerns for either fuel or manufacturing, but nuclear has an even more concentrated fuel supply chain than crude oil and natural gas, with only 3 countries taking up or producing most of the uranium around the world. And then for hydro, here I have no written for the vulnerabilities for fuel and manufacturing, but you'll see I've written this little asterisk here. And the main reason here is that because of climate change, there are significantly more droughts and there are changing precipitation patterns. And this could significantly impact the electricity generation potential of hydropower if precipitation patterns lead to the drying up of the water resources that hydropower plants were dependent on. And then for wind and solar and batteries, the fuel resources, or quote unquote fuel in this example, there is no fuel supply chain here. So there is no concern. But when it comes to manufacturing, there are a select number of, or a very small number of countries that mine the materials, refine the materials, and build out some of the components that are needed in wind, solar, and battery systems. So there is a very concentrated supply chain, similarly to how crude oil, natural gas, and geothermal have concentrated supply chains for their fuel resources. Okay, that is supply chain vulnerabilities. And now we'll go on to our last section here, which is health and environmental impacts. Now, before going into the table, I did want to go back over the definitions of these three here. So, air pollution is the contamination of atmospheric air by a toxic gas that can harm humans, plant life, and animal life. Greenhouse gas emissions are gases that trap infrared radiation within the Earth's atmosphere, and when emitted at a large scale, can lead to climate change. And then ecosystem disruption is an event that significantly alters the functioning of an ecosystem, which leads to the displacement or death of animals and plants in a region. So if we dive into the resources, we can see pretty easily here that coal has the worst human health and environmental impacts of all these energy resources. It emits a significant amount of air pollutants, it emits a significant amount of greenhouse gas emissions, and the mining process for coal leads to deforestation, and some of these, or I should say, some of these air pollutants here lead to acid rain, which can significantly harm agriculture and plant life in the nearby region of the coal-fired power plant. And then crude oil is similar, but does emit fewer air pollutants than coal, but it is still emits a high level of, air pollutants and greenhouse gas emissions. It does not lead to deforestation, but it also does lead to acid rain in nearby regions. Then natural gas is an alternative fossil fuel to coal and crude oil that has moderate it emits a moderate amount of air pollutants and a moderate amount of greenhouse gas emissions, and it also does lead to acid rain in certain regions. Then for geothermal, certain geothermal power plants will emit low levels of air pollutants and greenhouse gas emissions, but it is significantly lower than for the fossil fuels listed above. And geothermal power plants have minimal to no ecosystem disruption in their area, or in the area that they're built out. And then for nuclear power plants, they don't, during their operations, they don't emit any air pollutants and they don't emit any greenhouse gas emissions. But there is deforestation that does result from uranium mining. But I think one of the notes I did want to state here is that the deforestation from uranium mining is not nearly as widespread as it is for coal. So it's more problematic in the case of coal. Now, there are concerns around nuclear waste leakage, which would be important to note here. But nuclear waste leakage into the environment or into water resources has been largely mitigated across the world, at least as of today, as of this recording. And there's a great article from the nonprofit Our World in Data that shows the number of deaths from nuclear in comparison to other resources, and this is done on a per unit of electricity generated basis. And this very interesting article shows that the deaths from nuclear are significantly lower than that of fossil fuels, and they're actually on par with wind and solar. So I will add that article in our references on our website if you want to check it out. And then for wind, wind resources or wind power resources do not emit any air pollutants or greenhouse gas emissions during operation. And they don't have an ecosystem disruption, and I put a little star by there because there was something I wanted to mention. Across the world, but especially in the United States, there has been some publicity around wind turbines killing birds. But there is a great article written by a civil engineering professor at the Massachusetts Institute of Technology, and this article is titled, Do Wind Turbines Kill Birds? And this article explains that wind turbines kill about 0.02% of the birds that domestic house cats kill annually. So from my perspective, the problem of wind turbines killing birds is overstated in many news publications. Okay, and then for solar, there are no air pollutants and no greenhouse gas emissions during solar farm operations, but they can lead to deforestation, and this is because solar farms need a very large amount of land to capture the sunlight, and they require much more land than the other resources that we've discussed here. And so sometimes building out solar farms can lead to deforestation, but like discussed in the solar lecture, building out solar farms does require very careful consideration with competing land uses, such as agriculture, such as forestry, such as maintaining biodiversity in certain regions, etc. So if done in a smart way, solar farm build out can minimize the amount of impact on deforestation in the long run. And then for batteries, they are quite small systems. They don't generate electricity, so they don't emit any air pollutants and they don't emit any greenhouse gas emissions. And their footprint when building them out is very small, so they don't lead to any ecosystem disruption. All right, well, that is it for our comparison lecture, or our resource comparison lecture. This is the very first version of this lecture, so we are sure that there is much to be improved here. And if you have any thoughts, we would love your feedback. Do you think that something was not explained clearly enough? Do you think that there is a perspective or other information that we should add to this? If you have any of these thoughts, we will be adding a link to a feedback form, and after receiving a sufficient amount of feedback, we will update the lecture, we will re-record, and post the updated video. And so for all of for those of you who do provide feedback, thank you so much for helping us improve the quality of publicly available education. And also, if you found this lecture valuable, please consider donating. This helps us continue making publicly available educational content on the electricity industry. There'll be a link in the notes, but you can also visit our website at pearlstreetstudio.org. All right, this was our final lecture of our first unit, Generation Storage, which is part of our broader course, Introduction to the Electricity Industry. We hope you enjoyed this unit, and again, please give us feedback if you have any thoughts and opinions, and we will see you in Unit 2, Electric Grid Planning and Management.